Hi everyone, so in this video I'm going to go through the proof of the diagonalization theorem. So the statement of the diagonalization theorem says that if we let A be a square matrix in Rn by n with n linearly independent eigenvectors v1 through vn, so we're labeling these, with associated eigenvalues lambda 1 through lambda n. That is, we have each vi is non-zero with a vi equals lambda I vi. And if we define P to be the matrix whose columns are generated from the eigenvectors, and D to be the diagonal matrix whose diagonal is generated by the eigenvalues, then A is given by this decomposition. Okay, so to prove this is basically just a calculation using the properties of eigenvectors and eigenvalues. So on the one hand, we're first going to compute what AP is. Let's let x equal x1 through xn. And let's compute what APX is. So first of all, P is given by this formula. So Px is simply x1 v1 plus xn vn by definition. And so by linearity here, I have x1 a v1 plus x2 a v2 and that's just applying linearity of A. And then this is equal to, well, each vi is an eigenvector, so we can simply replace this with the scalar. So that's what APX looks like. On the other hand, what does PD look like? So I'll switch colors here. A PDX. Well, what does a diagonal matrix times a vector x give us? Well, it's just going to scale the first component by lambda 1, the second component by lambda 2, and so on. And then again, recalling that P is given by these columns, we again apply basic definition of matrix multiplication. So P times this vector is lambda 1 x1 v1 plus, if you like, you can relabel that y1 and then write y1 v1, but then y1 is equal to that. That's all I'm doing here. So I'm applying the same rule that I did above. Lambda 2 x2 v2 vn. But notice that this green expression, this here and this here, are the same. They're equal. So what we've showed is in fact that APX equals PDX for any x, right? So since it holds for any x, we have that AP equals PD. Okay? And then finally, this is the, so I'll go back up here with our assumptions. So Now I'm going to use this assumption here. So we have AP equals PD, but now I haven't used this assumption here, that I have n linearly independent eigenvectors. So now I'm going to use that. And why is that important? So since the set VI is linearly independent, the invertible matrix theorem says that P is invertible. So P inverse exists and APP inverse equals A equals PD P inverse. So you just need this linear independence so that the inverse of P exists, and so that you can multiply P inverse on both sides, and that's pretty much it. But basically the crux of this proof is simply show that AP equals PD through the properties of what it means to be an eigenvector and an eigenvalue, and then use the linear independence to simply then multiply P inverse onto the other side. And so at that point, you are now done with the proof. Thank you.